Hey there, and welcome back. Today, we're diving deep into one of the coolest ideas in all of chemistry, chemical equilibrium. And here's the secret. It's not about reactions stopping. Nope, it's about them finding this perfect, non-stop, dynamic balancing act.
So think about this for a second. What if a chemical reaction wasn't just a one-way street? A turns into B, the end. What if B could turn right back around into A? That one question, that's what cracks this entire topic wide open. We're not on a one-way street anymore. We're on a bustling two-way superhighway.
All right, so here's our game plan. First, we're going to break down what this balancing act really is. Then, we're going to play the role of disruptor and see what happens when we disturb that piece. After that, we'll learn how to keep score using a number called Kc, and then we'll actually solve a problem to put it all to the test. And finally, we'll see how this one idea literally helps feed the world. Let's get into it.
Okay, let's start at the beginning, the balancing act. What on earth do we mean when we say an equilibrium is dynamic?
Here it is, the official definition. Chemical equilibrium is that sweet spot in a reaction where the forward reaction, that's reactants becoming products, is happening at the exact same speed as the reverse reaction, the products turning back into reactants. It's all about the rate, the speed.
And this right here, this is so important because it clears up a huge misconception. At equilibrium, the rates are equal. But that doesn't mean the amounts of stuff are equal. Not at all. It just means the amounts have stopped changing. Their concentrations are now locked in. They're constant. That is a critical difference.
And that's exactly why we call it dynamic equilibrium, because nothing has actually stopped. Imagine a perfect tug of war. Both teams are pulling with exactly the same force. The rope isn't moving, right? But are the teams still pulling? You bet they are. There's a ton of action, just no overall change. That's our equilibrium.
Okay, so we have this perfect balanced tug of war. But what happens if what if we mess with it? What if we push it? This is where a super important rule of chemistry comes in to tell us exactly how the system is going to fight back.
And this is it. Le Chatelier's principle. You can think of this as the system's own personal rule book for dealing with stress. You push it pushes back. You pull it pulls back. It will always shift to try and undo whatever you just did to it. You can really boil it down to a simple three-step dance. First, you introduce a change, the stress. Second, the system responds. It shifts to counteract that stress. And third, it doesn't go back to where it was, but it finds a new balancing point, a new equilibrium.
Let's make it real with a pressure example. Okay, gases take up space, right? So if you squeeze the container, you crank up the pressure, the system basically says, whoa, it's getting way too crowded in here, and it'll favor whichever reaction, forward or reverse, produces fewer molecules of gas. It's literally trying to make more room for itself. So cool.
Now, it's great to talk about which side is favored, but chemists, we love numbers. We want to quantify things. So how do we put a number on this balance? Well, let's meet the official scorecard, the equilibrium constant, Kc.
The equilibrium constant, or Kc, sounds fancy, but honestly, it's just a fraction. That's it. You take the concentration of your products, put them on top. Take the concentration of your reactants, put them on the bottom. Do the division. That one number tells you the whole story of where that reaction likes to balance.
And reading that story is super easy. If your Kc is a big number, bigger than 1, that means the top of your fraction is bigger. You've got more products than reactants, so the forward reaction is favored. If Kc is a tiny number, less than 1, well, the bottom of the fraction is bigger. You've got mostly reactants hanging around. The reverse reaction is favored. It's that simple. Now, this next point is absolutely critical. There is only one thing, and I mean only one thing, that can change the actual value of Kc for a given reaction, and that is temperature. Messing with pressure or concentration will shift the system around for sure, but it will always resettle at the exact same Kc ratio. Temperature, though, that fundamentally changes the energy of the system, so it changes the balance point itself. Okay, enough theory. I think it's time we get our hands dirty. Let's take what we've learned and actually solve an equilibrium problem, step by step.
Look, pretty much every Kc calculation follows these same 3 steps. First, you write out the math expression for Kc, products over reactants. Second,
You use this awesome little organizational tool called a Rice E-table. It just helps you keep track of the reaction, the initial amounts, the change, and the final equilibrium amounts. Then, for the final step, you just plug the numbers from your table into the expression and solve. Easy.
So here's our challenge. We've got solid carbon reacting with carbon dioxide gas to make carbon monoxide gas. We're given a starting mass of CO2, the container volume, and the golden ticket, the concentration of CO2 once it hits equilibrium. The mission? Find Kc.
All right, let's build our table. First, we figure out the initial concentration of CO2 is 0.46. The problem tells us the equilibrium concentration is 0.054. So the change is simple subtraction. It went down by 0.406. Now, here's the magic. Look at the reaction equation. For every 1 CO2 that gets used up, 2 CO molecules are made. It's a 2-for-1 deal. So if the change for CO2 was minus 0.406, the change for CO must be plus 2 times that, which is plus 0.812. And since we started with 0 CO, its final equilibrium concentration is just 0.812. We have our numbers. We plug them into the Kc expression, concentration of CO squared divided by the concentration of CO2. So that's 0.812 squared over 0.054, which gives us a final Kc of 12.2. And boom, puzzle solved.
So why do we care? Who's actually using this stuff? Well, turns out these principles are the backbone of massive industrial processes that you rely on every single day. Let's look at maybe the most important one on the entire planet. Meet the Haber process. You could make a very strong argument that this is one of the most important chemical reactions ever discovered. It takes nitrogen right out of the air we breathe, combines it with hydrogen, and makes ammonia. That ammonia is the key ingredient in the fertilizers that grow the food that feeds billions of people. This is a big deal.
And check this out. This chart shows Le Chatelier's principle in beautiful practical action. As engineers crank up the pressure inside the reaction vessel from 150 atmospheres all the way up to 350, look what happens to the amount of ammonia you get out. The yield just keeps climbing.
And the reason why is sitting right there in the equation. Just count the gas molecules. On the left side, you've got 1 nitrogen plus 3 hydrogens. That's 4 molecules of gas. On the right, you've only got 2 molecules of ammonia. So just like we said before, when you squeeze the system with high pressure, it shifts to the side that takes up less space, the side with fewer molecules.
So let's boil it all down. What did we learn? 1. Equilibrium is this dynamic, nonstop balance of reaction speeds. 2. Le Chatelier's principle is our crystal ball. It predicts how that balance will shift when we mess with it. 3. Kc is the numerical scorecard that tells us where that balance point actually is. And 4. This isn't just textbook stuff. These ideas are used to make more product in some of the most important industries on Earth.
And that brings us to one last thought to chew on. If all these reactions are just this constant, dynamic dance, this endless tug of war seeking balance, can we really say that any chemical reaction is ever truly 100% finished?